Hello, welcome to lecture number 7. And in this lecture, we are going to look at another detector, which is the photomultiplier tube. So in a photomultiplier tube, what you have is the phenomena of photoelectric effect, which is at the heart of this device, wherein what you create is you have an impinging source of light. These impinging photons release electrons from the surface of a material, and these electrons are then are amplified or multiplied in the rest of the device. So let us first look at the characteristics of such a device. So the photomultiplier tubes can be operated in a variety of wavelengths, right? Of course, the original photoelectric effect was confined to the UV detection, visible and UV, but then now you also have materials that allow you to do near infrared detection. These are devices which are known for extremely high current amplification and accompanied with low noise, right? And hence these are extremely sensitive detectors. And if you think about what is the power level at which they can detect, something as little as 10 to the minus 19 watts of optical power can be detected by the photomultiplier tubes if one operates them in an optimal manner. So what I mean by optimal manner is that because I want to detect the extremely low light level of signal, I need to integrate for a longer duration of time, right? So if I do that, plus I ensure that I cool my photocathode such a way that this would decrease the amount of dark noise or dark count from my photocathode simply because the thermally released electrons would be minimized. So that way it would help. The other thing which is very quite interesting is that one is able to do something called the pulse height discrimination. What it means is that I have an input flux, remember, of signal, um, and you see, the signal, the photoelectrons which are generated by the signal are eventually amplified to give you a pulse of current. Now, if the number of photons which are coming in are large, the proportionately the photocurrent, the eventual amplified current also is large. So one can discriminate and sort of put a cutoff, which will not look at, for example, the uh, signal arising out of dark noise, right? So one can do this pulse height discrimination at the output level to basically figure out and count only the signal. Now, I mean, so this improves, my signal to noise ratio in to a certain extent. All right. So, and clearly, you know that the photocathode material has got a spectral dependence. That is you know that you require a minimum amount of energy with the photoelectrons for the photoelectrons to be released from the surface. If the photons do not have that h nu minimum or the lambda max, you will not be releasing the photoelectrons from the photo cathode material. Now the materials of usually of variety of kinds with variety of possibilities for work functions. So for example, metals have a work function of about 4.5 eV, so one can detect UV and so on. But there are these other compounds which have got low work functions. For example, this silver oxygen cesium or antimony cesium and so on. So these are uh, materials which have got low work function and are used basically to as photocathode material in the photomultiplier tube. The most important mm, characteristics apart from the generation of photoelectrons itself is that these electrons need to be focused and accelerated. So essentially in the photomultiplier tube, you would have electrostatic lenses that focus the electrons and also accelerate them because it gives sufficient potential energy difference, or you basically create an electric field along the direction of propagation, uh, you know, uh, uh, along the direction of propagation of the electrons, so as to provide to them extra kinetic energy with which they impinge on various intermediate surfaces called dynodes and create many more um, uh, electrons. That is how the multiplication process happens. So this focusing and acceleration is very intrinsic to this functioning of the photomultiplier tube, and hence the name photomultiplier, as in multiplication. And this process is basically repeated about 8 to 10 times, right? And I will show you with a schematic in the next slide. And this is what results in this large multiplication of an extremely small signal, comes out as a reasonably strong current pulse, even though my input flux is extremely weak. So here is a schematic. This is a schematic of a photomultiplier tube. You have the incoming photon, which needs to have sufficient photon energy itself so as to overcome uh, the work function associated with that material, which is a photocathode material. So there is a window behind which there is a photocathode material, and when the light impinges on it, it releases an electron. Now these electrons are, as I said, focused and accelerated, between this electrode here and this electrode here. So the typical voltage between this is about hundreds of volts, and that leads to acceleration of this electron along this path. Again, these electrons hit here and they release many more electrons. And typically, for example, if the multiplication factors, let's say for every impinging electron, you release 5 of them. So you see that 5 electrons are now again refocused onto the next terminal. These terminals inside are called dynodes. Okay. And they each of those will release 5 more, because the potential difference is still about 100 volts between two. So you see there's a successive potential drop of 100 volts which is being there between these dynodes, and this process basically keeps multiplying. So extremely weak signals here actually result in an extremely large current pulse at the output. So eventually you have the anode, which collects the whole current, and that is what is basically measured in the output. So imagine that my, each the multiplication factor for each electron was 5, let's say, and every time for every one of them, this happens n times. So this is delta to the power of n. It becomes now the overall multiplication factor after it has gone through these n dynodes. So imagine that this was about 9. You would quickly build up this to about a million, a factor of a million, right? So this is the kind of great gain and the multiplication of the electrons, which is what the photomultiplier tube is known for, and hence is an extremely sensitive device. So now let's look at the intrinsic, mechanism. So again, I'm looking at pictorially. What you have here is the conduction band associated with the material, right? Where this is a sea of electrons which are there. And of course, they cannot leave the surface of the material because there is an energy to be overcome. This surface energy which needs to be overcome is called the work function. By vacuum level, I mean that these are the electrons which will become free from the material, right? That's the minimum energy for it to become free. So you need to provide this energy to the electron by the external photon. So h nu is the energy associated with the photon. It basically impinges on the material and releases this electron only if the h nu is equal to or larger than the work function, right? So this is the limit of the frequency, minimum frequency with which you can basically detect, right? Remember, phi here is the it symbolizes the work function and not the photon flux here. So this is literally a particle detector, single photon detector, if your photon has sufficient energy, right? So the typical voltage can vary from hundreds of volts to about 400 volts, and of course the gain, hence the gain can be sort of tailored, by varying this intra dynode voltages, right? So imagine so between the first dynode to the last one, imagine about 10 of them, you basically have a 1 kilovolt difference. So these are devices which require high voltage for their operation, right? So imagine that there are n dynodes. I'm simply repeating my argument, and the average multiplication factor for the secondary emission, that is the input electron would photoelectron would come from the photocathode, fall on the first one, it would generate a delta number of secondary electrons. Each of those secondary electrons will go to the next dynode and generate, each one will generate delta, and this becomes basically delta to the power of n, depending on how many times this process happens. So as an example, I already told you about this. So imagine that my voltage was 400 volts, then you see the delta happens to be about 10. That would mean that my 10 to the power of 9 is already, you get a billion times more number of electrons than you released at the first level. So you see that clearly this is extremely high gain device, and clearly you know that there is a gain bandwidth product. That would mean that uh, when this avalanche of electrons are being generated, it would require certain time for the avalanche to get over. Within that time, essentially the detector is not operational, so that is kind of a dead time. So you see that if I demand for sensitivity, then I would have to compromise on the dead time because I require more time for the avalanche to build up, and vice versa. If I have more input, right, and I demand less sensitivity, I can probably quench the gain. So there is always going to be, the speed at which I can operate, which is related to bandwidth, and there is going to be gain, and these are going to be always going to be such that one has to play one against the other, and hence look at a optimal operation, which is a compromise of the both, or depending on what you basically want from the detector. So now let's look at the heart of it, which is the noise mechanisms. So clearly there is going to be a cathode short noise, right? Because you see, uh, there is a average current I can associate with the photocathode signal itself. That my signal is coming in with this average current, but there is also a dark current. So because these are extremely sensitive devices, so you see that random thermal excitation of electrons can also lead to generation of that electron from the photocathode, right? And similarly, there is always a background of cosmic rays, right, which is coming from the sun, for example, our nearest star. There is a radioactive background which is always there on Earth. So, right, so all of these actually have sufficient energy to basically drive the dark current in this. So even when my device is completely off, I would see basically get this, dark current. What I mean is, even when my signal is completely off, I would still get this dark current, which is basically released from this other extraneous sources of energy, right? So this, you can clearly see that uh, this is my the usual expression for the short noise. But of course, you see that the current is multiplied. We are looking at power now, so that is multiplied by G square, where G was the gain, right? So what you have is, a very large number. For example, if I had a 400 volt difference, then I had a billion, but now this is now going to be 10 to the power of 18, right? That's the kind of, the factor that will, the noise will dramatically increase, this short noise, and that is going to severely limit, my signal detection. Now, just like there is a short noise because of the fact that the electrons are being released in this uh, packet individual discrete manner. Absolutely similarly, the secondary electrons also are released in this discrete random manner, right? So there is a randomness associated with the secondary emission as well that creates its own short noise. But you see that this is being created at the various dynodes, okay? And then so what happens is the current which is arising out of this short noise is actually arising somewhere midway in the path. It is arriving at the first dynode, the second dynode, the fifth dynode, and the ninth dynode. So if you look at the total contribution of this dynode short noise, it happens to be 1 over delta times the cathode short noise, okay? And hence it is typically ignored. So for example, if delta was 10, remember I gave you the example of the 400 volt between the dinodes. So then you see that this noise is going to be 1/10. After all, the randomness affects only the future events or the multiplication of the noise. So hence it does not contribute uh, so dramatically to the randomness of the initial process itself, and it is the initial emission of the photoelectron that contributes the largest in terms of the cathode short noise. The other, of course, noise is the Johnson noise, and this is basically related with the fact that when the current comes out, you need to drop it across a resistor. There is always going to be a dissipative element, and this particular thing one has to associate an appropriate temperature with that process of getting the output, and this would be the Johnson noise contribution to the photomultiplier tube. Now, remember we had used, for example, the heterodyne detection earlier to get to something called the quantum limit of optical detection. Same heterodyne technique is very widely used for photomultiplier tubes, and so I will not repeat that discussion uh, on the heterodyne detection using the photomultiplier tube. The arguments exactly go in a similar manner. What one does here is basically mix the signal with the local oscillator, and then the two gains, the signal as well as the noise. You see that the short noise goes away because that becomes my dominant noise, and so on, and one can get to the quantum limit. So a different sort of a detection technique is called the video detection that is applied to photomultiplier tubes, which is different from the heterodyne detection. But again, let me emphasize, heterodyne detection is still the most preferred and widely used technique to obtain a quantum limit of optical detection. Right. So the video detection has the following setup. What it has is that your input optical wave itself is modulated at a low frequency. How do you do that? You could probably put a chopper in your input signal. The optical wave is coming. You put it through a chopper, so which is chopping the light periodically. That is going to modulate the input signal, right? So this is done at just prior to detection with a known low frequency modulation. So what happens is now that my amplitude of my signal, which was my signal was Es cosine omega st, that amplitude gets modulated, right? M becomes my depth of modulation, omega m is that low frequency modulation. So my amplitude itself gets modulated uh, in this manner when it falls on the detector. So of course the detector, of course, measures the mod square of this. So this is my signal at the detector, and the photocathode current is proportional to V times V star. Remember, we are looking at the square law detector. So, and there is this proportionality constant A, which I can write down as A times Vt square. I'll have to go ahead and again try to fix it. At the moment, it's unknown. So you see, this is the form that you get for the current which is generated, photocurrent which is generated at the photocathode because of the input signal. So now if you carefully open up this and look at the various frequency components which are inbuilt in it, right? Imagine so you have 1 plus some cosine omega t and a mod square of it. There is going to be a DC part, right? This DC part is basically depends also on the depth of modulation. So in the case of perfect modulation, M will be 1, for example. There is a term that is dependent on the frequency at the incoming modulation frequency itself, and there's going to be another term which is at twice the modulation frequency. So right, you have these uh, separated uh, components in the frequency space which are centered around DC, centered at omega m, and also centered at twice omega m, right? Twice the modulation frequency. So you see, carefully, one can now put in, band filters and pick up the signal of your choice, right? So that is what one does. And the way to, for example, fix that prefactor A, right, would be to basically set my modulation to 0. And I know that this is my input power. So input power by the energy of individual photons, right? This is H nu S is correspond to the signal photons energy. This will give me the rate at which photons are impinging, and uh, if average amount of photocurrent, so this is the rate multiplied by eta will give me the efficiency with which electron is generated, right? Because eta is giving me the ratio between the number of electrons generated divided by the number of input photons, right? So this quantum efficiency multiplied by the charge of the electron will basically give me the average photocurrent arising from the signal, right? So you see that I know that this is true. That would mean that if I want to fix A, I just put my M to 0, right? And if I put my M to 0, I would basically, get IC of T, and that prefactor A, I can clearly identify. You will see that it is essentially just E eta by H nu S. So that one can put in here, and hence I have got rid of my A, right? In the manner similar that what we have discussed earlier. So this is what you get. Now what you do is you basically filter out the signal at omega m. There's a signal at DC, there is a signal at twice omega m. So I put a band filter and filter out the signal at omega m. And clearly you see that this signal is going to be proportional to the power in my input signal, right? It's clearly proportional. It's proportional to m itself. In case of perfect modulation, I'll get 1. And this is basically, proportional to the input power. So this is how I can isolate a particular band with a bandwidth, let's say delta nu, about this omega m, and I would get my the current associated with my signal. And I have multiplied by this factor G to basically tell you how the multiplication process across this photocurrent is what is getting multiplied by a factor G, and that is what I am basically going to this is what is going to contribute, this current is what is going to contribute to the noise as well, which is the short noise. So the short noise I can get essentially, my IC bar, which is the average current arising from the signal itself, and you have ID, which is my dark current. So this becomes my corresponding short noise for such a input signal. Now remember, the gain is also happening for the DC component as well as for the twice omega m component, right? Both of these are happening. So let us not think that it's only localized only there. It is not. It is it is just that one is using a band pass filter to pick out uh, the current which I'm interested in, which is proportional to my signal power, right? So it's question of identifying that particular bandwidth and only looking at that and filtering out the other, right? That is what one has done here. All right. So there is also the other component, right? So we have ignored the dynode contribution. The other contribution is coming from essentially the Johnson noise. So this TE, as I told you, the temperature, the effective temperature of this setup is chosen so as to account for the thermal noise as well as the noise generated in the amplifier, which is following the photomultiplier tube, right? I can have another amplifier. So that effective temperature associated with that noise is what is put in here. So my signal to noise ratio is basically the signal itself, right? Divided by the short noise coming from the short noise at the cathode, the photocathode itself, and the Johnson noise, right? And so you see this Johnson noise is basically sitting in here. We have ignored the dynode noise because that was 1 by delta of this short noise contribution. And so you see, when my current is when my gain is large in my system, the Johnson noise is not really dependent on the gain, right? It is not the thing that is getting multiplied in this manner, but it is the G square factor that basically makes these two terms on the numerator as well as the denominator, the first term in the denominator, to dominate this system. So now you see that clearly you'll see that my G square can sort of dominate, and hence I can signal to noise ratio, these can get actually cancelled. And there is also a very interesting thing which I would tell you, that let's assume for a moment that I'm looking at extremely low light levels of my input signal. So my average current is really small, and it so happens that my average current is typically even smaller than my dark current, and I will show you with an example that this is indeed true. So let's assume that and see what we get as the noise. So uh, you will see that if I now set my signal to noise ratio to 1. Why? Because I am saying I want to look at my limit of detection, just like the exercise we have done earlier for other detectors. So I'm setting my signal to noise ratio to 1, and my statement is that if my input power is equal to the noise, that is my P minimum, that would be my limit of detection. So P minimum would be that limit, and you see that on the numerator you have a G square factor coming from the signal, okay, whereas in the denominator you have the dark current that is dominating. So the signal short noise is gone away, I ignored it, dark current is what is remaining, and if I come up with this is the uh, P minimum I get, right? So in principle, if I could ignore or eliminate basically dark noise and the Johnson noise completely, so that the only contribution is short noise, then one can basically get the average photocurrent IC bar, and then I will get my quantum limit of optical detection, right? Just like we had got for the heterodyne. But you see, this is impossible to eliminate dark noise. Dark noise is coming out of the background thermal excitation, from cosmic radiation, from the background radioactivity on Earth, and so on. So we have no control over this dark noise. Okay, hence, you see, the way out of this is actually to do heterodyne. And heterodyne is what is practiced for one to get this quantum limit of optical detection, even for a photomultiplier tube. So, this kind of elimination of noise is impossible in video detection, but it does get to be pretty good. But it is not sufficient to get to uh, the quantum limit of optical detection, which tells me the minimum possible signal that I can, in principle, detect. Uh, and the heterodyne would be a way to actually do it in a practical, efficient manner. All right, so this was about video detection wherein you are modulating it. So now let me look at a concrete example, to get our numbers and bearing. So the typical, by the way, the efficiency of photomultiplier tubes is only about 10 to about 25 to 30%. That is the best you can get, right? So the efficiencies are really limited in comparison to our semiconductor devices, which can have very large quantum efficiencies. Yet it is used simply because the large gain that happens. So imagine that I am looking at optical frequency excitation about 500 nanometers. The bandwidth as standard I'm taking as 1 hertz. Imagine that my dark current was about femtoampere, 10 to the power minus 15 of ampere. By the way, this is a typical value of it. So if you look at this typical value of this dark current, plug it in the expression that I had in my previous slide, and you see that the P minimum I would get is about 3 to the power minus 16 of a watt. This is the minimum I can detect. Now, if this is the minimum, what does it tell you? It tells you what is the corresponding average cathode's current, right? Average current which I am detecting. So average current happens to be of the order of 10 to the power of minus 17 of an ampere, right? So you see clearly the signal is much weaker. Average current through the signal is much weaker than the contribution coming from the dark current. So clearly our dark current being much larger, at least 100 times larger, was indeed a good a reasonable approximation that we did to get to that expression of the P minimum, right? So this is how uh, the photomultiplier tube, the video detection, and of course the ideal being the heterodyne detection, which again you can repeat that argument for the photomultiplier tube as well. So before I go ahead, I want to basically dwell a little bit on this quantum limited optical detection, right? These are just basically fundamental arguments that tell you why it works the way it works in terms of the Poissonian distribution and so on. So remember, it is arising. What we are doing is we are trying to make the detection process being dominated by the short noise. And once you have done that, one can basically try and get to the quantum limit of optical detection, right? So look at this. I'm basically uh, uh, going to give you a very overview of that argument, very fundamental argument. So imagine h nu is the energy associated with my photon. Now remember that the average photon, power in my optical signal is basically telling me the rate at which the photons are arriving. So this is my number of photons per second multiplied by the energy associated with one photon. Right? This will give me energy per unit time because this is looking at a rate of arrival of photons. Um, Now you see that there is a quantum efficiency associated with this particular detection process that basically tells me the what is the number of electrons that will be generated for every input photon. So uh, even in the best noiseless hypothetical situation, right, hypothetical noiseless situation, my detector, the PMT, the photomultiplier tube, produces exactly one electron for 1 over eta number of incident photons, right? That's a way to think about it. So the measurement involves basically counting the number of electrons in a given time t, right? So imagine in a given time t, I have got the number of electrons that will be emitted would be what? It is the number of photons, right? per unit time, the input flux, times the time period will give me the number of events which are happening, and the chance at which these are going to be turned into electrons is basically now giving me the the number of electrons which are generated within the time capital T. Right? This is my average number of electrons arising out of the noiseless conversion of the electron of the photon into a current which I am detecting. So the photons are arriving, remember that in a random manner. So they actually themselves obey Poissonian statistics. So imagine that my detection process was definite. Even then, I would get this Poissonian distribution. And uh, there is a Poisson distribution, remember, in the influx of photons itself, and there's a Poisson distribution of the creation of photoelectrons at the photocathode surface. So either way, you're going to get the Poissonian distribution. So here what I assumed is that there is no randomness in the incoming photon flux, right? And hence this definite, and the generation of the randomness is only in the process of release of the photoelectrons and not the incoming photon flux. Remember that. All right. So if I am now looking at the RMS square average, if you like, then I to just basically look at the number of electrons across various events minus the average and whole square, and then average over uh, the Poissonian statistics, if you like. This happens to be simply it is proportional to the average number of electrons itself, which by the way is simply n bar, which is the input flux of photons, times my t, which is the time duration within which the influx happens, and eta being my quantum efficiency. Now you see that if I am looking at the RMS fluctuation, then I take a square root of this quantity, right? And so RMS fluctuations are going to be square root n t minimum times t times eta square root. If this is equal to my input signal, right? That is right. My P minimum is equal to the RMS fluctuation. That is what is my P minimum. So I'm just putting in these factors as it is, right? The square root comes out from the Poissonian statistics, um, standard deviation, right? So if this is equal, then I can rearrange this and I get the following, right? I get my n minimum, that is the minimum number of photons that I need, that I can detect, would be equal to 1 by t times eta. Now remember, t is my detection time, which is same as the inverse of the bandwidth. So I can essentially write down my p minimum, right, as basically h nu times n minimum, right, which is basically h nu times eta times t, where t is basically the bandwidth. So you get this very fundamental dependence that is coming out of simply the Poissonian nature of the photoelectron generation. Now imagine the Poissonian nature was in the incoming photon statistics. I would not be able to distinguish by looking at this, you know, whether the Poissonian nature, the randomness is arising from the incoming photons or from the generation of the electron process. And this is what something that we deal with in quantum optics. We will see that if you want to worry about the randomness or look at the statistics of the photons themselves, I require a certain threshold minimum of the efficiency of my detector to actually mm, pin it down to the randomness of the photons instead of the randomness of the photoelectrons which are being generated itself. So you see, there is going to be there is always that uncertainty as to where the randomness is coming from, and one has to worry about it if one wants to look at the randomness in the photons themselves, which is intrinsically coming in my signal, if you like, versus the randomness in the process of detection itself at the photocathode surface. And this is true for all kinds of processes, including what happens in a PN junction, a photo conductive device, or any other for that matter device. As I told you, detection is intrinsically a statistical phenomena.